Yeah.
Last time, I think you were probably 30, 40 minutes into it.
Okay, so this is a typical alternating current sine wave. In this case, it's symmetrical. And it goes from a peak voltage of one polarity to a peak voltage of the opposite polarity, which we're representing as the V peak up here. So the voltage peak to peak is going to be twice that. Now you notice this dashed line, which we call the voltage RMS. And that means that's the equivalent DC voltage that would produce the same amount of heating in a resistor. So in your house, you've got 120 volts AC, more or less. That's actually 120 volts AC RMS, which is the root of the mean of the squares of those. That is just a way to calculate the area under the curve. So in essence, if you chop the top off where that dashed line is of both of these, flip the bottom one up, you would fill it in and essentially get this 0.707, which is 1 over the square root of 2, which is a thing you should remember. It pops up a lot. Either the square root of 2 or the reciprocal of the square root of 2. When we talk about frequency, it's just a measure of how many cycles or times the waveform changes polarity. And we now represent that in hertz after, what was his name, Rudolph? Anyway, we used to call it cycles per second, which was a whole lot easier because when you do some of the math, you want to come out in seconds and hertz is not obvious, but hertz is equivalent to a cycle per second. Now you also have the period of the waveform, which is the reciprocal of the frequency. So if you divide the frequency into 1, you will get the period in seconds, which is how long in time that it takes to complete one cycle. Now this is a phasor diagram. Remember, a phasor is a little bit different than a vector. A vector is a length from some point in space to another point in space. A phasor is a length at an angle, and we usually plot those on a polar chart. In this case, if we look at the circle, and we've some time ago decided there's 360 degrees in a circle. And as we rotate the radius around, okay, you can actually generate this sine wave. So if you, in this case, they're showing it every 30 degrees. So if we have the radius, let me turn this back on, this one, at 30 degrees, and we looked at the sine function for that, which would be the height at that point, here to here. And we plot that on a degree scale, it would come out at this point. If we do 60 degrees, it comes out here. If we do 90, it comes out here. And we plot these all the way around, and we will actually get a sine wave, which is how they're generated by that cyclical motion. Now, we call each of these angles in here phase. So in other words, this is a 30-degree phase angle, 60, 90, 180, which would be half of the waveform. Now, when we get into, and you don't need to know this for any of the amateur exams, but they made me learn it in college in engineering, and it turns out it's a lot easier to do some of the math when we talk about radial velocity. So if you think of a circle that has a radius of, say, 1, the circumference of that circle is going to be 2 pi times that radius. So regardless of what the radius is, the circumference is always going to be 2 pi. So we can say that 2 pi radians, if we call the radius a radian without a length, would equal the circumference of the circle or represent a complete waveform. So in a lot of the equations you'll see, you'll have a 2 pi f showing up. And that's where that comes from, is there's the frequency is how many of these cycles there are per second. The 2 pi represents how many radians per cycle. So if you have a fraction of a cycle, then you're going to get a fraction of 2 pi radians, like pi radians, pi over 2. Just so you know where that stuff came from. Is that any clearer, or is it like mud?
Nope.
Okay. Now, one of the things when you increase frequency is that you decrease the wavelength. Again, it's a reciprocal function. It's like period. And you also increase the energy in the waveform. It takes more energy to generate a high frequency waveform than it does a low frequency one. I mean, it's just like, just think about waving your hand slowly and then waving it as fast as you can. It takes more energy to wave it as fast as you can wave it. So in this chart, we're showing where radio waves appear in the overall spectrum, and everything between DC and gamma rays, whatever's above that, are all electromagnetic waves. So radio waves are down at the lower end, and then we get into the infrared light, ultraviolet, X-rays, and gamma rays. And it's these ultraviolet, X-rays, and gamma rays that are the high energy waves, which when we talk about propagation, those are the things that affect the atoms in the upper atmosphere and the ionosphere, and can actually energize the electrons and create the ions. So, as an example, what is the period of a 60 hertz waveform? Would be the reciprocal of the frequency. I just showed how to, the formula is frequency is equal to 1 over the period. So the period is going to be equal to 1 over the frequency. So it turns out it's 0.01667 seconds. If we wanted the frequency of a waveform that had a 1 microsecond period, you play with the same formula and it's going to be 1 megahertz. Morning, Ernie.
Chair, Ernie, I'll grab it for you. I get it.
Oh, he wants his good chair?
One where I can sit for a little bit.
Okay. Oh, that's a nice chair. I want that chair. I'm going to get that next time. This one keeps me awake. Okay, the next thing besides frequency and period is phase, which we talked about a little bit. And in this chart, I'm showing the blue waveform, which is just standard sine wave that is, let's say it's in phase. The yellow or gold, however that shows on your screen, is that same waveform shifted by 90 degrees or a quarter of a cycle, which would turn out to be pi over 2 if you're doing radians. Oh, and I forgot to mention when we do radians or radial velocity, we represent it with the sign omega, which is like a little funny W, which represents 2 pi times the frequency. Just so you're familiar with it, and this is actually what Nikola Tesla actually patented, was polyphase power. And in today, we basically use 3-phase power for transmission. So each of the 3 voltage lines has a different phase shift waveform. So it's very easy to drive a 3-phase motor with that, and you get less current. That's much more efficient for power transmission. That's not on the exam.
And they're all 60 degrees out of phase.
120,
60.
120.
Depends on how you look at it.
Well, the waveforms are 120 because it's got to be 360, and there's 3 of them.
But there's 6 plus and minus at 60.
Yeah, but
degrees,
that's
60.
one waveform is plus and minus.
Yeah.
The peaks are 60 apart.
That's what I'm talking about.
Okay. But the waveforms are 120.
Yes.
Okay.
Okay. Depends on how you,
Right. Everything's relative to how you look at it.
right.
That's what Einstein said.
Yeah,
Yeah, he did.
I thought that was only fast speed.
Yeah. When you go fast, things look short.
Mhm.
Okay, so I was trying to come up with some questions on this. Not sure how to phrase it, but how many phase degrees are there in half of a complete waveform? So if there's 360 degrees, I gotta turn mail off between the next shear. The half cycle is gonna be 180 degrees of phase shift. And remember, there's 2 pi radians in a complete cycle. So one of the other parameters is wavelength, which you will use a lot, and there will be questions on the test about wavelength. Particularly when it refers to antennas. And it's the distance traveled during one complete cycle of a waveform when the waveform is moving at the speed of light or some fraction thereof, because it only travels at the 300 million meters per second when it's in a vacuum and free space. When it's traveling through air or another gas or a metal, it travels much slower. In some cases, I think the velocity factor is down to like 0.6. It depends on the medium. Oh, and then it's even talking about velocity factor. So wavelength is different than period because period is the number of seconds of the waveform. Wavelength is the distance that the charge waveform actually moves. And we do that in meters. There's also a formula to convert it directly to inches. But all you have to do is remember that there's 39.4 inches in a meter. Okay, so what would the wavelength of a 7.074 megahertz radio signal be? That's my favorite frequency.
42 megs. 42.
42.4 meters.
Yeah.
It's in the 40-meter band. Now, if you notice when we talk about in amateur radio, the different bands, you know, the 80, 40, 20, 15, 10. If you plug those into the wavelength formula, they don't exactly come out even like they should. It's an approximation. So even though this is 42 meters, we call it the 40-meter band. So what's the frequency of a 20.201 meter wavelength signal? We use the same formula where lambda is equal to 300 divided by the frequency in megahertz. And I guess I should mention the reason it's simplified, instead of using 300 million meters per second divided by the frequency in hertz, we can cancel out 10 to the 6th. So we get 300 divided by the frequency in megahertz. So we do 300 divided by the 21.2 and get 14.150 megahertz, which is kind of in the middle of the 20-meter band.
So just kind of jumping down and looking below, we're talking about when you add in the velocity factor. So the assumption is the velocity factor is always going to be a constant of 1 unless stated otherwise.
It's going to be a constant of 1 as long as you're in a vacuum and free space.
Okay.
Anytime it's traveling in something else, then you apply the velocity factor.
But you apply that to lambda.
Yes.
Okay. Okay.
Well, actually, you apply it to the 300.
Right.
Okay, because it'll be a fraction of the 300. Now, when it's traveling in like copper, I think it's about 0.95 or somewhere
It varies.
a little.
So a given substance or material like copper is going to have an associated velocity factor. What you're saying?
Right.
Okay.
And that will be affected by, for instance, what kind of insulation is on the wire, whether it's bare wire or it's got insulation on it.
Right.
And
The diameter of it too.
right, the diameter can affect it.
Okay.
With the skin effect. You'll mostly
Hey, so curious though, Robert, though, as we're going through, and I'm just, if I don't mean to distract you though, but
no, that's
as
problem.
we're going through, the velocity factors will normally be given, or will you ever be faced with a problem that you actually have to calculate the velocity factor?
No, well, okay. On the exam, there will be possibly a couple questions, and you will have to know what the velocity factor is because they will tell you that it's a certain type of coax.
Ah, okay, gotcha. All right.
And there's about, as I recall, there's about 3 of them that are used.
But I'm assuming,
The 0.8 something and 0.65, I believe.
right, but I'm assuming by that time we'll be familiar with the different velocity factors, right?
That low.
Say that again?
I'm assuming by that time there'll be a known variety of velocity factors that we'll just be accustomed to using,
Oh,
right?
yeah, yeah.
Okay.
You know, and that'll, you know, that's in the technician exam or in the class, and we talk about those basic ones, so you just have to remember a couple.
Gotcha. Okay, that's all I had. Thanks.
Okay. In a lot of those cases, with some of the problems, the answers are far enough apart that even if you don't apply the velocity factor, you'll be close enough
Correct.
to guess the answer.
Exactly.
I think
Yeah,
the one I'm
you'll be
thinking
able,
of, I think it comes out 19 meters. And when you do the velocity factor, it's like 18, and I think that's what's on the answer on the exam.
which
But
is
all
close
the
enough
other
to get you to
options
the
are
right answer.
much different. And that's the other
Exactly.
thing. On the exam, most, particularly if it's a problem, there will be at least two of the answers that are way out of the ballpark.
Exactly. Far enough out that you'll throw it
Right.
out by
And the other two
logic.
won't be close enough that, just kind of doing the math in your head, rounding off. I mean,
Yep.
it'll be the correct one.
Yep. Gotcha. Thank you.
Okay, so what did we learn? Alternating current continuously changes direction. Frequency is the number of times current changes direction per second, represented by small f usually, and we now use hertz. Phase is a fraction of a complete cycle in degrees or radians. And we use the theta Greek symbol to represent the phase angle. So when we talk about power factor, I don't know if I go into this. No, I don't think I do. But power factor comes up in some of the exam questions, probably on the general. I don't remember technician doing power
I don't
factor.
remember any power factors in the technician, but general and
Right.
Nashville.
And then wavelength, which is the distance traveled by the wave, depending on how fast it's going. So it's going somewhere equivalent to the speed of light or less, depending on the medium.
Yep.
All right, where did I?